All right, you recall from the title of this chapter, it's called Capacitance and Dielectrics. So, what is dielectrics? Well, you know, when we calculate numerical values of capacitance, and oftentimes you see that, you get a very, very small value, right? Not farad, but rather, millifarad. Millifarad is already pretty big. Microfarad or nano, even picofarad. How does one try to increase the capacitance? Okay, that is certainly an important task. What if you need a bigger capacitor? What do you do? Well, we can always increase the dimension, right? Make it bigger and bigger, but that is not always practical. Is there another way for us to increase the capacitance? Well, let's say the charge contained on each of these two plates is given, Q and negative Q. Capacitance is defined as Q over V. V is the difference in voltage between these two plates. Okay, so C is defined like that. In order to increase C, Q cannot change. Okay, in order to increase C, I must decrease V. Right? To decrease V means I must weaken the electric field in between these two. So, is there a way one can somehow decrease the electric field, weaken the electric field between these two plates? That would directly make V smaller, which means C will be increased. So, is it possible, for example, to insert some special substance in between these two plates? So it's not vacuum anymore. Rather, we insert a certain special material such that once you insert this material, you find there is a drop in the electric field between these two plates, and that makes V smaller, and that will make C greater. Well, it turns out, yes, we can do that, and that there is a class of material that does that, and these are called dielectrics. Okay? In particular, if I insert a piece of dielectrics to fill this air gap, okay? As a result, when you measure V, you find V would drop by a factor. Okay? Would drop by a factor, and as a result, C will increase by the same factor. Okay? And this particular factor, we call it the so-called dielectric constant. Dielectric constant. So V goes to V over the dielectric constant, and the symbol for the dielectric constant is kappa. It looks like a K, but it's a Greek letter, not Latin letter. It reads kappa, not K. Okay, kappa is called dielectric constant. It is a numerical value. Okay, it doesn't have any dimension. It's just a number. Okay. With that, C is now equal to Q over the new V. The new V is the original V over kappa. Okay, let's say the original V, we call it V naught. So I move that kappa over. That's Q over V naught. That is the original voltage difference. So Q over V naught is original. It is the original capacitance without the dielectrics. So it is now kappa times C naught. Okay, kappa times C naught. So you see, by inserting this piece of dielectric, the voltage decreases by a factor of kappa, and therefore the capacitance increases by a factor of kappa. And if kappa equals 100, for example, you have effectively increased the capacitance by a factor of 100. So, how does that work? Well, the reason why V decreases by a factor of kappa is because the electric field gets weakened by a factor of kappa, right? So it is really because the electric field changed. If the original electric field is E naught between these two plates without the dielectrics, and if the new electric field is E with the dielectrics, this ratio, of course, is equal to kappa. Okay, in fact, this is how we define kappa. That's how we define kappa, the dielectric constant. So this dielectrics is able to weaken the electric field by a factor of kappa. How does it work? Okay, what is the physical mechanism behind it? Well, the reason why for all electric fields, we have learned so far, at least, there is only one source that creates an electrostatic field, and that is what? An electric charge, right? Now, you have Q and negative Q. That's still there. So these two sources did not change, but you insert a piece of dielectrics which is charge neutral overall. Okay, you find that the electric field changed. It weakened. It gets weaker, and that means there must be some charge distribution here. within this magic piece of material called dielectrics, which changed the total charge distribution of the whole setup, and therefore changing the electric field, weakening the electric field. Okay, in particular, the original field E naught goes like this, right? From the positive to the negative. The dielectrics must have its own charge distribution so that it produces a counteracting field, right, in the opposite direction, so that when you add these two fields up, you get a net field E, still pointing the same way but a lot weaker than before by a factor of kappa. Okay, how does one produce a uniform field in that direction, opposite to the original field? Well, in the original case, we have a positive plate here, a negative plate there. So how about if I have some sort of positive charge distribution here on this edge of the dielectrics and some sort of negative charge on the other edge? Now that would have done the trick, right? Because first of all, if this charge and that charge cancel out, then the whole piece is still charge neutral. It's not charged. And secondly, this charge and that charge certainly would have produced a backward field, which would tend to cancel the original field, therefore weakening the total field by a factor of kappa. And so now the only question is, how does it introduce a layer of charge here and a layer of charge there? Remember, the whole dielectric is charge neutral. It is not a conductor either, okay? So therefore, you cannot imagine electrons flowing back and forth to establish such a layer of charge here, layer of charge there. It is made of insulators, okay? Insulators. Now, what's an insulator? It's a material in which there are no mobile charge carriers, no electrons that can move freely from place to place. All the charges are bound to individual atoms. They cannot move from one atom to another atom. Okay? Now that doesn't mean there is no electrical response for an insulator at all. It can be made of molecules that are polarized. Remember the idea of electric dipoles? Okay, electric dipoles. So each molecule in the dielectric material can be polarized. Let me show you. Okay, electric dipoles. So that means the positive and negative centers of this molecule may not coincide. So imagine here is a molecule. Okay, here's a molecule. I simplified in the form of dipole. So here is a positive center of the molecule, and here's the negative center of the molecule. They're not coincidental, so you have what's called a dipole. And this dipole has a dipole moment, as we saw, we defined in chapter 23. It's like this, okay, pointing from negative to positive. It's got a dipole moment. Now you put this dipole in an electric field. What's going to happen? Well, the net force on the dipole is 0 because the dipole receives one force due to the positive charge pointing it this way, and it receives another force on the negative charge pointing in just the opposite direction. And since these two charges have the same magnitude, these two forces cancel each other out in magnitude as well as in direction. But in general, these two forces do not act on the same line, right? This guy goes this way, this guy goes that way. They are misaligned, okay? So you have a pair of forces like this, equal in magnitude but opposite in direction, and yet there is a distance between them. Okay, this is called a force couple. You may recall that from physics 1A, or you may not, but here it is, force couple. A force couple cannot accelerate the center of mass of this whole piece because the net force is 0. And yet, what do you think it can do? Well, it can turn it around, right? It can exert a torque on this thing. So as a result, this charge will move this way, that charge will be moved that way, the whole thing is going to turn, okay? As it turns, eventually, the dipole will be oriented like this, okay? Will be oriented like this, and I can redraw the positive charge and the negative charge, okay? And now the dipole will be aligned along the direction of the original existing electric field, right? So that's what the electric field does. It doesn't move the dipole from place to place. Rather, it flips, it turns it around, so the dipole is now aligned. Okay, it is now aligned along the direction of the electric field. So suppose you have a whole bunch of dipoles. Okay, you have a whole bunch of dipoles. Each one of them, under the influence of the existing electric field, will be aligned. That's after you have the electric field. So before the electric field is there, before the electric field is established, each dipole will just point randomly in whatever direction, randomly, because there is no preferable direction for the dipole to point. If you look at the whole piece, what is the electric field produced by all these dipoles? Because of the randomness of the orientation of the dipole, will be zero. Will be zero. But now you turn on an electric field like this, an original field, and that field will then cause the dipoles to turn. Now, under ideal circumstances, each dipole will be totally aligned along this direction, just like this guy. Okay. In reality, the alignment is not perfect. There are always some dipoles that will misorient, but more or less, in general, the dipoles will be somewhat aligned. Okay, will be somewhat aligned. So you're looking at a situation like this. You're looking at something like this, something like this. Okay, the alignment is not perfect, but it's Now, if you take a look at this situation, okay, look at this row of dipoles, right? 1, 2, 3, 4, and so on. This positive charge and that negative charge, they're pretty much close to each other, so you can think of them as canceling each other out. But you look at this whole block here, okay? What happens on this surface? What happens on this surface? Pretty much you get only heads, right? You get only heads. So, and the heads are positive charge. So, on this surface of the dielectric material, you're going to have a layer of positive charge. These are actually heads of the dipoles, okay, other molecular dipoles. And what about that side? Well, these are mostly tails that you're getting. The tails are negative charge, so you get a whole bunch of negative charge on the other side. And in between, the dipoles are pretty close to each other, the positive and negative pretty much cancel each other out. You don't have to worry about it. So effectively speaking, this dielectric material, once you put it in the presence of a uniform electric field, would behave as a positive layer of charge on one end, a negative layer of charge on the other end. And you see, this pair of layers will produce an electric field in the opposite direction, because here is positive, here is negative. So it goes like that. You see, here's the original field, here's the field induced by these dipoles, and that tends to cancel the original field, and therefore the electric field is now weaker than that single field before. That is how dielectrics work. So basically it's just a collection of molecular dipoles. Okay, and if the alignment is really good, then you can imagine the field is stronger here, so the backward field is stronger here, and then the total field will be much less than before. So kappa will be great, will be large value. As a matter of fact, there is a table, table 1 in chapter 26. It tells you values of kappa for different materials, which you can take a look. Okay, now first of all, what is the value of kappa for vacuum? Vacuum is really nothing. There's nothing there, right? If there's nothing there, is there any electric dipole that can help you reduce the original field? Of course, no. So, E and E naught should really be the same, right? And therefore, what do you think kappa should be equal to? By definition, for vacuum, should be exactly equal to 1, okay? That's by definition. Now, what about dry air? Air is not a vacuum. It's got stuff in it. It's got air molecules. And the air molecules can be polarized. They're not very effective, but they can be somewhat polarized. So you will produce a weak backward field. So you do not get a lot of cancellation of the original field. So you put an electric field in air, there will be a slight decrease in the total electric field due to the alignment of air molecules backwards. So kappa is somewhat greater than 1, but very close to 1. Okay, so the electric field, which is original electric field divided by kappa, will be very close to the original electric field, but not by much. Will be somewhat smaller, but not by much. So kappa for air is 1.00059, as you see from the table. But if you look at other materials, and especially if you look at water, okay, that's interesting. Water, kappa equals what? 80, okay? What does that tell you? It tells you that if you put an electric field, whatever that is, okay, in vacuum, and all of a sudden you put some water in between, okay, you introduce some water, you find the electric field will be greatly reduced to only 1/80th, that's less than 2% of the original field. Okay? Water is a very good dielectric because what happens is that water molecules, H2O, are highly polarized. Okay, so they're very effective polarizers. You put water, suppose this is a block of water. You got original E field, and the alignment of the water molecule will be quite efficient so that they will produce a pretty strong backward field, which almost cancels the original field, leaving less than 2% of the net field. That is how dielectric works in the case of water.